Okay, great. So in the last couple of weeks, we have been talking about essentially data modeling, right? So that's the process that take as input the application you actually want to build in real world, and try to think about how to build a database schema for that application. And we talk about different levels of modeling, right? So on one hand, the first step is what's called conceptual modeling, right? So you take as input this application, and you try to describe all the entities and all the relationships that you have in this application. And one way to do that is by draw an entity relationship diagram that look like this, right? So every single rectangle here corresponding to an entity site, and every single this diamond shape corresponding to a relationship among those entity sites. So once you have this, you have a very, very precise way for you to tell a computer or tell other people, right, what is really the application that you are kind of trying to build here. And in the last lecture, we talked about how to translate this conceptual model into a logical model. A logical model is something that you have in relational database as a relational schema, right? All your data represent a whole bunch of relations. For example, have student relation with this schema, right? So think about putting data as something like a table, something like that. And we talk about this process, right? On the left-hand side, you have this entity relationship diagram, which precisely give you a whole bunch of logical sentences that your data must satisfy, right? That's how to think about conceptual model. And then you do the translation, right? So entity sites become relation, and the relationships also become relation. And then we talk about how to pick a suitable key after the translation, right? The way to think about it is on the left-hand side, you have a whole bunch of constraints in your model. On the right-hand side, we want the same set of constraints to be enforced or to be satisfied. And for some of those constraints, you can actually enforce it using, for example, primary key, right? For example, for the last constraint, right, if you set the primary key of the relation R to the combination of A and C, right, essentially you are enforcing the last constraint on the left-hand side, which essentially tells you if I know the value of A and C, it's uniquely associated with a value, or with a tuple in this relation R. But there could be other type of constraints that you cannot enforce via the schema in the logical model. For example, the first constraint, the second constraint, and the last lecture we talked about how to enforce them by actually defining like integrity constraints inside your database. For example, for the first constraint, you can enforce that using a foreign key, like as a foreign key constraint. For the second one, you can just add, for example, unique constraint on the schema of R. So today we are going to talk about the next step. Okay? So you have your conceptual model. You do the translation of the logical model that enforce all of the constraints that you have. So far, we know how to do that. So what's next? What's next in reading about how to build a good data schema for your application? So I think we all remember there is one step after you do the translation, which is try to reason about whether you should merge two relations or not. And that's going to be something that's going to motivate we are going to talk about today. So let's just refresh our memory, okay? So you see this, you saw this slides before, a couple of weeks ago, right? We have this entity relationship model, and we have employees, and we have departments, these two entity sites, and we have a relationship works in connecting these two entity sites. So how to do the translation, right? The very first step is you have employees as a relation, right? You have departments as relation. You have the works in relationship as a relation. So you have three different relations. So if you look at these two relations, works in and employees, right? So their key, right? Primary key will be the social security number, the ID of the employees, right? For example. And then we could actually merge that into a new relation. Looks like this, right? So I can have the works in relation being kind of subsumed by the employees relation, right? I can put whatever department this employee works in into the employees relation, right? And we could do that. And we actually talk about what is the benefit or disadvantage of doing this type of merging. And we could go another way, right? And the same conceptual model. You could merge this works in relation with the department relation. Department relation has a primary key as department ID. And then you can put whatever department associate, you can put, like whenever department appears in the works in relation, yeah, you can also put in whatever information you have about that department. You could merge these two relations into this one. So clearly, this probably will not be a good strategy because there's a whole bunch of data redundancy that you have that could potentially hurt you here. So intuitively, we know how to reason about these two different designs. The first one, right, makes sense to merge them, right? The second one probably doesn't make too much sense to actually merge them. We all have this intuitive way to think about data redundancy. And whenever there's a data redundancy, we all have an intuitive way to reason about whether it's good or not, right? You guys are very smart. I mean, I'm really confident that intuitively you understand like how to reason about it. But we will not be happy about that because we want to make sure the system knows how to do it. We want to make sure an user of the database system who are not as an expert as you guys knows how to think about data redundancy and whether we can make this process of trying to reason about whether we can merge different relations together be a process that's as systematic as possible. So to do that, we should actually think about, how should we think about data redundancy, right? So how can we define it, and how can we infer data redundancy, and what's the implication of different type of data redundancy to your database design, right? And then how should we precisely think about merging and splitting relations in your logical design? And that's something we are going to talk about today, and also next lecture and the next Wednesday, using these 3 different lectures to talk about what people often call the database design theory. The fundamental thing is you have an application. You could have different ways to design your logical schema. You could merge these two relations. You could split this relation. Right? You have so many different ways for you to store the same piece of information. And the core of the database design theory is really try to understand precisely what is a good database design and how to formally model and enforce the property that we want in a good design. So as a very first step in understanding what a good design, so today we are going to talk about something called functional dependency to really give us a tool and a language to talk about data redundancy in your data. So before we start to formalize it, let's refresh our memory and get on the same page about what are the things we do not like about data redundancy and what are data redundancy you could see in real world. So now let's look at this database schema, okay? So this is the schema with a whole bunch of information. I have the first attribute is the ID of the student, and then I have the second attribute is the course that student take. As you can see, if the student 1 is taking 3 different courses, it's corresponding to 3 different roles in this relation. And the third attribute is the grade that student get in this course, and then followed by the name of students and address of students, for example. So what are the problems about this schema? Yeah, so exactly, right? So there's the student's information being stored multiple times in this schema. And then it could introduce a whole bunch of anomalies. For example, because the address information as student side, right? So being stored multiple times, there could be update anomaly, right? What if one student change address, right? In this case, you need to update all of those appearance of that address, right? So if you miss any of those, you end up have a database with kind of inconsistent data, which could be very hard to fix. And you could have, for example, insert anomaly, right? When you are adding a new course, right? So when the students take a new course, right? You kind of need to remember, okay, I also need to put in the address of the student. If you think about that operation, right? Most of the users who are updating the student and the course relationship probably don't really care about the address, probably don't really think about I need to also insert the right address and right name for that specific student, right? So there could be insert anomaly. And then there could be delete anomaly, right? For example, you could have one student only taking one course, right? And they'll say, okay, the student dropped this course. What should you do? You cannot delete that tuple, right? Because once you delete that tuple, the information about the address for the student also gets lost, right? The student just drops the only course the student has, right? So student should be somewhere in the data, in the database. And all of those anomalies, right, are caused by data redundancy. It's because you have two pieces of data. You have the student and course information, and then you have student and address information. And the problem is that you start to fuse these two pieces of information into the same relation, and you end up duplicating the student address information multiple times. And because of that, there's a whole bunch of data anomalies that we could have in this schema. So intuitively, we don't like this. Okay? We do not like it. We think it's a very bad schema. We are going to discuss how to process define it. But intuitively, this is something that we do not want. So there's a whole bunch of problems associated with data redundancy. The first thing is, it's a waste of storage space. I think this one is very natural to see, right? So in this relation, we are storing the same piece of information multiple times, right? But then you need to have additional work to really keep these multiple copies of information consistent, right? You need to have multiple updates. You need to be really careful about it. You need to have additional code, right, to really make this kind of consistent, right? Somebody need to implement that logic. When you have multiple people interacting in the same database, right? So it's very hard to enforce that. But on the other hand, right, we talk about why we do not like redundancy. But there could also be cases that we actually want redundancy. Okay? So now let's look at this example, right? So same example. Can we think about some scenario that we want to introduce redundancy into the data, right? So in this case, for example, it's very unlikely for this specific example you want to introduce this type of redundancy. But in many cases, introducing redundancy could also make your application faster, right? So for example, if every single time I'm loading the student and course relation, the student taking this course, I have to fetch the address of student anyway, for whatever reason. But if that is your workload, then this schema actually starts to make sense. Because then you do not need to join these two relations together every single time you use that piece of information. You can just sequentially scan this relation, right? Whenever I have the student and the course, I have the address with me, right? So if you have a workload like that, sometimes introducing redundancy could give you some benefit, right? So, and especially for today, when memory and the disk becoming cheaper and cheaper, right? So the trade-off between the storage and the performance start to shift. But the fundamental trade-off is whenever you have redundancy, you waste space, and on the other hand, you also need to do extra work to manage those data consistency. But on the other hand, potentially, you have better locality for these two pieces of data. If you are running a specific type of workload, it could be faster. But anyway, what we are curious about is how to reason about data redundancy, how to define it, and how to do inference of data redundancy. So that is what we are curious about at this moment. So how to model it and how to reason about it. So there are different types of data redundancy. So as you will see, maybe next week, you are going to see a very different type of data redundancy compared with what we are going to look at today. But what we are going to talk about today is something called functional dependency. let's just formally define it. So what is functional dependency? And also how to do inference about those functional dependencies. Okay, so let's try to define it. Assuming you have a schema look like this, I have a relation R with 4 different attributes, A, B, C, and D. And each one of them have their own data type, their domain, DA to DD, something like that. And what is a valid instance of this relation? A valid instance is like this. It's a subset of this collection of tuples, right? That satisfy all those type constraints, right? Whatever subset of tuples satisfied in this type constraint is going to be a valid database instance. Let's call that R. If you pick 2 subsets of attributes, okay? Let's call them alpha and beta, okay? So they are subset of attributes, A, B, C, D, I mean subset of those. So we see there's functional dependency from alpha to beta. We all say like alpha decides beta, okay? We say there's functional dependency from alpha to beta if and only if the following hold. That is, if you take any 2 tuples, R and S, in this relational instance R, as long as their alpha attributes matches, it implies their beta attributes will also match. If that hold, we say alpha decides beta, okay? Or there's a functional dependency from alpha to beta, right? And you write that in this notation. You have alpha followed by the arrow and followed by beta. So essentially, right, if alpha decides beta, right, then for any 2 tuples in R, you have this relationship. So the way to think about it, it is as if there's a function mapping in your data that actually maps a specific value in this column alpha to the value of your attributes beta. So that is why it's called a functional dependency, and that is how to think about it. So we have this notation, okay? If this functional dependency is satisfied in this specific database instance. So this is pretty abstract at this moment, but intuitively it makes sense, right? So we want to, if there's 2 subsets of attributes of the relation alpha and beta, alpha decides beta, it means that for any 2 tuples, if they have the same alpha value, then that implies they have the same beta value. Okay? So let's look at a concrete example. So we have this relation here, R, with 4 different attributes. Let's try to find all functional dependencies in this relation instance. So let's look at the first one. Is there a functional dependency from A to B? Okay? A is a subset of attributes which only contain 1 attribute, the first one, and whether the first attribute decide the second attribute. How should we think about that? Right? The way to think about that is go back to definition. What do I mean by this? What do I mean by this functional dependency from A to B is, in this relation instance, if I know the value of A, okay, that's going to decide the value of B. That is what I mean by this. So the way to check it is by picking every pair of tuples in this relation R. And you'll see, do you have a case that these 2 tuples share the same A value but have a different B value? If you can find such a pair, then of course A doesn't decide B, right? Because knowing A doesn't tell you which B it is. Then you do not have this functional dependency in this relational instance. If after checking all the pair, you do not find such example, then you can say, yeah, in this relational instance, this functional dependency holds. So now let's look at our functional dependency A to B, right? So, and let's try to check it. The first tuple is A4, right? So, and B2. in this relation, I do not have any other tuple with A4 in the A attributes, right? So I should be fine. I take all the pairs involving the first tuple. I never have the case that it shares the value of A, right? So yeah, so that implication will trivially hold because the left-hand side is false. And then I take the second tuple. I say, yeah, so the A value is A1, the B value is B1. It shares the same A value as the third tuple, right? So they have the same A value as A1. So I check the B attribute to say, yeah, they're the same, right? If I know it's A1 for A attributes, I know in this instance, the attribute of B will also be B1. You cannot find the case where A equals to A1 and B equals to something else in this relation instance. So it's fine, okay? And you go to the first tuple, you have A2, right, which is unique in this relation, so it's fine. You have last tuple, A3, unique in this relation, it's fine, right? So you check all the possible pairs of tuples, and then clearly in this case, the functional dependency that A decides B hold for this. Make sense? Any questions about this? Okay, so it's very important to get this clear because this lecture is going to be pretty theoretical. It's very important to really get on the same page what we are talking about. Now let's look at the second functional dependency. C and D as a combination decides B. Okay? Yeah, in this case, right? So our alpha in the definition is C and D, this subset of attributes. Beta is B, right, on the right-hand side. So again, how can we check it, whether this hold or not, right? So in this case, it's the same, right? And the way to check it is you look at every single pair of tuples, and you'll see, yeah, can I find a pair that shares the same value on C and D, but have a different value on B? If that is the case, then this doesn't hold. If you enumerate all the pairs, then it holds. Okay? So in this case, you can do this exercise by yourself, right? You cannot find any. So if you look at this, only the first tuple and the fifth tuple, they share the same value of the combination C and D, right? They all have C4 and D3. You look at that, and you'll see, yeah, whether they have different B value. Does this specific CD value really decide B for me, right? In this case, you say, yeah, so the first tuple is B2, the fifth tuple is B2, so it's fine, okay? In this instance, if I know the value on C and D, I know the value of B, okay? You can do this exercise by enumerating all the possible pairs, but this one holds. Now let's look at the third one. In this relation instance, do I have B decides C? Well, I mean, again, you enumerate all the pairs, right? So, but when you start to enumerate the fourth tuple and the fifth tuple, you start to see a problem. In this case, all the B value are B2. And then if you look at the C value, right? One is C3, another is C4. In this case, you have the two tuples sharing the same B value, but have a different C value. Essentially means that in this instance, if I know the value of B, it doesn't decide C. It could be C3, it could be C4, I have no idea. Okay? And that is a pair. Because of that, we do not have the functional dependency that B decides C in this relational instance. Make sense? And when that doesn't hold, we write that symbol I don't know how to describe. Okay? So, makes sense. Any questions? You have any question, just make sure we answer that at this moment because it's going to become pretty abstract really fast today. Yeah?
Is functional dependency, is that prescriptive or descriptive?
What do you mean by that?
Well, do we get the table and then we see if there are functional dependencies, or do we say there have to be functional dependencies?
Oh, yeah, so that's a very good question. So for this example, right, you are trying to find all the functional dependencies that hold in this relation instance. When you define a schema, you can say, this is all the functional dependency that must hold for whatever data you put here. And the way that you check is if you give me a new relational instance, whether that satisfies the functional dependency or not. So it can go both ways. Okay? Any other questions? No questions? Okay. So a convention of writing this, right? So for example, if you look at the second functional dependency, so I say CD decide B, right? So I always write that bracket, right, notation, right? Sometimes it gets really, really messy. So we just write CD to B, right? So like the thing that you see on the slides, instead of having the bracket, right? I mean, it's just a shorthand of notation, okay? Now let's look at another example. So this is a family tree, right? So I have the child, first attribute. I have a father, I have the mother, I have a grandmother and grandfather. Okay? And I put family tree here. For this instance, right? So can we find all the functional dependencies? If you fuse this piece of data into this relation, right? What could be all the functional dependencies that we have here? So in this case, right? So if you look at child and father and the mother, okay? So it's essentially in this relation instance, once I know the child, I know the father and the mother, right? So I cannot find two tuples about the same child but corresponding to different father and mother pairs, right? In this case, the first functional dependency is there in this piece of data. And if you look at the section of the second functional dependency, whether child and grandfather decide grandmother. That's also true for this piece of data, right? Once I know the value of the child and the grandfather, I cannot find another tuple with a different grandmother. Okay, make sense? And similarly, you have the child, grandmother decide grandfather. Make sense? This is the three different functional dependency that actually hold in this piece of data. Again, the way to check is very simple, okay? So I just, if you want to decide whether alpha to beta is here, you enumerate all the possible pairs. You see whether you can find a pair that share the same alpha but different beta, okay? So the notion of this is very similar to functions. That's why it's called functional dependency, right? For example, you have a function to say, yeah, this is a function that takes as input the child and output the father, right? When you do that, and the carrier will say, yeah, because the specific child decide the father, I cannot have the same child give me two values, right? Because that's a function, right? So in this case, you are actually trying to describe the same thing. Potentially, you are telling me for these two different specific subset of attributes, there could be a function connecting them, okay? So that is what we are trying to say with this. Once you have the notion of functional dependency, you can start to define a whole bunch of kind of concept that we had before using this language very precisely. We talk about the notion of keys, right? So we talk about the keys, right? So that is, we define it in a kind of vague way, right? But now we can make that pretty precise. So we can define what is a superkey, right, in this relation. That is, superkey is a superset of a key, okay? So assuming you have alpha, which is a subset of attributes in the schema, it is a superkey, or superset of keys, if and only if there is a functional dependency from alpha to the full set of attributes, okay? Here we write R there means all the columns in R. So it's very easy to see why, right? Because if I have in this relation instance, or like in this schema, that a functional dependency from alpha to all the attributes, it means that you cannot find two tuples in this relation sharing the same value on alpha, but different for any other attributes. And that is a key, okay? So in this case, right, alpha is a superset of key if and only if you have this functional dependency from alpha to R. Make sense? Okay. So a second condition of something being a key is it needs to be minimal, okay? It needs to be the smallest subset, right? So that uniquely define a tuple, right? So in this case, what do we mean by minimal? we say alpha to beta, alpha decide beta, this functional dependency, okay, is minimal if and only if I cannot remove anything from the left-hand side, okay? Which means for all attributes in alpha, if you remove that from the left-hand side, then this functional dependency doesn't hold anymore, okay? That's what we mean by minimal. And then this gave us, I mean, you could use this notation. You have functional dependency plus a dot to say it's a minimal functional dependency, right, from alpha to beta. So once you have that, you can precisely define what is a candidate key. A candidate key of relation is a subset of attributes alpha that minimally decide all the attributes, okay? If alpha is a candidate key, it means that the following functional dependency hold. That is, A decide the R, so A decide all the attributes. On the other hand, this one need to be minimal. That is, I cannot remove any attribute in this candidate key that this functional dependency still hold. Make sense? And this actually is a very precise definition about what we mean by something is a candidate key. Make sense? Any questions? So far, so good? Okay. So now let's look at one example. Okay. So we have this relation describing, for example, all the towns in Switzerland. Right? So you have the name of the town, you have the content of the town, you have the area code, and you have the population of the town, for example. Right? Let's say these 4 attributes fit together into a single relation. Let's try to find all the functional dependencies here. Let's think about it. What are the functional dependencies here? So first thing we could have is the name of the town plus the content of the town, right? These two together decide the area code and the population, right? So that seems to be true and also makes sense, right? I mean, you cannot have the name of the town decide area code because you could have, for example, 2 different towns sharing the same name and different content have different area code, right? So, and that doesn't hold. But if you have the combination of name and content, at least for this relation, probably, I think, holds true in reality, right? Going to decide the area code, going to decide the population. Okay? That's one functional dependency that actually holds in this piece of data. Okay? So second is if you take the name of the town and also the area code, right? So that decide the content and the population, right? Which also hold in this piece of data. You cannot find 2 tuples with the same name of the town, with the same area code, but mapped to 2 different content, right? Which doesn't hold in this piece of data, right? Which also weird in reality, right? So if you have these 2 functional dependency in this data, you can start to automatically decide what is a key or what is a candidate key for this relation, right? So in this case, what could be candidate key? The first candidate key could be the combination of name and content. Why? Because there's a functional dependency from name content to area code and population. Essentially, this combination of attributes decides everything else. And it's a minimum. Why? Because I cannot remove the content. It doesn't, and then functional dependency that doesn't hold anymore. I cannot remove the name. So this is minimum, and there's a functional dependency from this subset to the whole set of attributes. So again, the second thing, candidate key could be name and area code, right? The same type of reasoning, right? So once you have this collection of functional dependencies, in principle, you can start to reason precisely in a systematic way what are all the candidate keys you have in this relation. So another place where functional dependency can appear is when we talk about cardinality in entity relationship diagram, right? So in this case, right, just refresh our memory, right? So now we have the lecturer, professor, and department, right? 3 different entities connected by this teaches relationship, right? So professor teaches this lecture in that department, for example. And we have this one-to-many notation, right? So we have the N for lecture, 1 for professor, 1 for department. And what do they mean? So when we talk about this, right, so we define this, actually we define this pretty precisely, but in a very long formula, if you remember, essentially we say, yeah, for every single one in the ER diagram, I essentially say, if I know the value of lecture and department, I know the professor who is teaching it, right? So it cannot map to 2 professors. If I know the value of lecturer and professor in this relationship, I know the value of department. And the mathematically precise way to talk about what do we mean by that is to say, once you have this entity relationship diagram, what you are saying is, okay, whatever data that is valid in this application must have these 2 functional dependencies that hold. The first functional dependency is from professor and lecturer to department. Okay? The second functional dependency is from department, lecturer to professor. For every single one in the entity relationship diagram, you introduce 1 functional dependency you are assuming for your application. That's precisely what we mean by this one-to-many relationship, like notation for this cardinality thing. On the other hand, you do not have the third functional dependency if you have that entity relationship diagram, right? So I do not have that the lecturer decide department and professor, right? Simply, that's not semantic of that notation. So as you can see, the notion of functional dependency really connect closely with the concept that we have been learning so far, right? Once we have this precise way to think about dependency, we can now describe very precisely what are superkeys, what are candidate keys, and what are we really doing when we're defining cardinality in my entity relationship diagram. So it's useful, could be useful. But what's also more important, it also gave us a very systematic way to inference about data dependency. For example, now I know a key of a relation need to satisfy a certain condition. That is, there need to be a functional dependency from the key to the whole set of attributes. How can I check that? If you give me an input as a collection of functional dependency that you know is going to hold, how can I automatically reason about all the possible candidate keys in this relation? So that is what we want to achieve. To do that, we need to think about how to do inference for functional dependencies. How we come up with all the functional dependencies that will hold here, given an input collection of functional dependencies. So it's going to be a lot of fun. So what are we trying to do? The input is a set of functional dependencies, F. Okay? Set of functional dependencies that we know is going to hold. What we want to do is let's try to find new functional dependencies that's not in this input site, but it's kind of implied by the input. Okay? If your input hold, then this new functional dependency, even though it's not in my input, will also hold. So that is what we are trying to do by talking about inference. So fundamental question look like this. Is if you give me a relation and you say, these are all the functional dependency I know is going to hold, we want to say, yeah, if I give you a new functional dependency F to beta that's not in F, will that also hold given F? Okay? So if you think about why you want to do this, is whenever you are drawing this ER diagram, you are defining a whole bunch of functional dependency, right? And then I will ask you, is this attribute a key for this relation? Then you have a very precise way of checking that. You can check whether the functional dependency from that, for example, alpha to R, is really hold, given all the functional dependency that inside your ER diagram, right? That gives you a very precise algorithm about how to reason about candidate keys in your logical design. So again, for any logical inference system, there are always 2 different ways for us to define what do we mean by something hold. Okay? There's always the syntax, and then there's the semantics. It's the same thing as when you are learning first-order logic. You have that separation between syntax and semantics. Here we have the same thing, right? Because we can define differently what do we really mean by function dependency actually hold. And by what do we mean by one functional dependency is implied by a collection of functional dependencies. So there's always a syntax and there's a semantic. On the semantic side, if we say, if f hold, then alpha to beta will also hold. In the semantic sense, what we are actually saying is, can we prove for all possible relation instance R that satisfy f, it will also satisfy alpha to beta. Okay, this is from semantic side. On the syntax side, we write with a different notation. So to say the syntax, we say whether we can derive alpha to beta by applying a set of inference rules over f. It's very similar to first-order logic, right? You have syntax, you have semantics. Okay, so and for functional dependency, this is what we mean. Any questions? Is a separation between syntax and semantic clear? Do you still remember, like in your first year, right? So there's a first-order logic, there's a syntax, there's a semantics, and then they are both complete and sound, right? Still remember that, right? Any question about this? Okay. So the way we are going to do this, as we are going to see today, is by introduce an axiom system for you to derive new functional dependencies purely from the syntax, from a given collection of functional dependencies. And then we are going to prove that inference system, even though you only consider syntax, is both sound and complete. That's going to connect this syntax, this inference system at syntax level with the inference system at semantics level. The fundamental result is there exists an axiom system that if you can derive alpha to beta from f in a semantics way, okay, meaning that for all the possible relation instances that satisfy f, you can prove that it's going to satisfy alpha to beta. If this holds, it's equivalent to you can derive it using a whole bunch of inference rules giving f as the input. So that's the fundamental result we are going to talk about today. Okay. So more precisely, we can define this in a more precise way about the inference process that we are trying to do. So let f be a set of functional dependencies on schema R. And let alpha to beta be another functional dependency on R. Okay? We say f implies this new functional dependency if for every single relation instance R of the schema that satisfy all functional dependencies in f, it also satisfies alpha to beta. And then once you have this, we can define the notion of closure of f. Okay? So essentially, f is a set of functional dependency on schema R. The closure of f, we write it as f plus, is a set of all functional dependencies that can be implied by f. Okay? So that's pretty natural as a definition, right? You have f. This is all the other functional dependency implied by your input f. And if you have two different sets of functional dependencies, for example, f and g, we can also define their relationships, right? We say they are equivalent, right? If and only if you can, if and only if two things hold, that f imply g and g imply f. Okay, make sense? So one thing that we are curious about is whether there's a systematic way to compute the closure. Okay, and is there a systematic way, right, for us to check whether a new functional dependency is in the closure or not? So that is what we are curious about. To do that, it's very hard for you to do inference at the semantics level, because that need to, you need to enumerate all the possible relation instances and prove, oh, if this hold, that will hold. Luckily, you can do the inference at the syntax level. And that is by defining a collection of inference. Sorry, because talk about theory is running out of time. Okay, so let's take a break. We'll be back in 15 minutes to continue to talk about theory. Yeah. Okay, so let's continue. Can I get a signal from Zoom? Can you hear me? Okay. Great. So we were talking about how to do inference of functional dependencies. Right? We define what do we mean by that. Right? What do we mean by a collection of functional dependency imply a new one. Right? So from a semantic way. And our goal is like most of the logical system, we want to define something you can actually derive from the syntax and try to prove its soundness and completeness. And for functional dependency, Armstrong's axiom actually gave you such an inference system. It contains like only few very, very simple inference rules. So first inference rule is called reflexivity. Essentially, it says that if I have two different collections of attributes, alpha and beta, if alpha is a subset of beta, then I know that beta decides alpha. Okay? So it's the first inference rule in this axiom system. If you think about it, it makes sense, right? So I have a subset of attributes, and that's going to decide the whole set of attributes. Sorry. Yeah, sorry. The whole set decides the subset, right? If I know the value of this larger collection of attributes, that uniquely decide the value of this smaller subset of attributes, right? So this is the first inference rule in the Armstrong axiom inference system. So a special case of that is you can take beta, the superset, as all the attributes in this relation. Then you can have that R, right, the full set of attributes, decide any subset of attributes you have in this relation. So, and we call this one trivial, okay? Yeah. So the first rule gives you a whole bunch of trivial functional dependencies. Okay, so remember the word trivial because down the road when we talk about trivial functional dependency, we mean this type of functional dependencies. Okay, that the right-hand side, that the left-hand side is a superset of the right-hand side. But even we call it trivial, even it looks simple and just makes sense, right? So we have more, right? So this is just one specific axiom in this system. So the second inference rule is called augmentation. And it looks like this. It says that if I have a functional dependency that alpha decides beta, I can pick any other attributes and put that on the left-hand side and put that on the right-hand side. And then alpha gamma decides beta gamma will hold. If you think about it, it also makes sense, right? So, and here, like remember the notation, when we write alpha gamma, we mean alpha union gamma. It's going to take all the attributes either in alpha or in gamma, okay? So that's a notation thing. So third axiom is transitivity, which essentially says that if you have two functional dependencies, alpha decides beta, beta decides gamma, then alpha decides gamma. Okay? Also, like makes sense. The three very simple axioms and inference rules in this inference system. And what's fascinating about it is the inference system that's actually constructed by these three very simple rules are both sound, which I think we can agree, right? Whatever being inferred by this inference system is going to be correct because it makes sense, right? We are going to prove it, don't worry, but they make sense. But probably more surprising is they are also complete. That is, all the valid functional dependency rules that are going to hold given your input set of functional dependency can be derived by applying these three very simple inference rules again and again and again. And that is probably the surprising part of this equation. So let's talk more about this. Let's take the first rule and reason about whether it's really sound or not. I mean, it makes sense intuitively to us, but don't trust anyone without the proof. So it's very simple. Look at this. How can we prove its semantic soundness? What do we mean by that? We mean, yeah, if I have f and the alpha to beta, right? So assuming I can use this rule to derive from syntax level a new functional dependency, that means that for all the relation instance that I could construct, this functional dependency will hold at semantic level. So how can we prove that, right? So let's try to do this. So assume you have, alpha is a subset of beta. That's what we are given, right, on the left-hand side in the rule. So what we hope is whatever relation instance you have are, if you take any two tuples, T1 and T2 in this relation instance, if they match on beta, that implies they also match on alpha, right? If you can prove this, it means that I can apply this rule to derive a new functional dependency. But on the other hand, for all the relation instance you can construct, this functional dependency will hold. Okay? So that actually connects this kind of inference at the syntax level to your semantic. So that's what we are trying to do. Essentially, we want to prove this. And that's kind of easy to prove, right? So you have T1 and T2, two arbitrary tuples, right, from the relation, assuming they match on beta, which is the superset, all the attributes on beta matches between T1 and T2, right? So assume they doesn't match on alpha, which is a subset, right? So it's kind of easy for you to construct, there must be an attribute, right, C, right, in alpha that these two things doesn't really match, right? But because alpha is a subset of beta, C must belong to beta, so beta shouldn't match. You have contradiction. Then you have T1 alpha equals to T2 alpha. Alpha also need to match because simply a subset, and then you are done, right? So again, there's nothing fancy in the proof, right? It just tells you this inference rule at the syntax level is actually semantically sound. Whatever functional dependency you derive by applying this rule is actually semantically correct. Okay? The second one, we can do the same exercise, augmentation. I have alpha to beta. I add gamma on both sides. So how can you prove the soundness? Then it becomes a little bit more interesting. So the way that you prove it, again, prove by contradiction. So you assume that you have alpha to beta, hold. Okay. What does this mean? It hold means that for all the possible relations you can construct, this one hold. Okay. So assume this hold. And then you assume alpha gamma to beta gamma doesn't hold, it's false. So let's assume that and see what we can derive out of it. Because you have alpha to beta, alpha beta decide beta gamma, alpha gamma decide beta gamma is false semantically. It means that there must exist two tuples, T1 and T2, that following hold. That they must match on alpha and gamma, which is the left-hand side, but they do not match on beta gamma. Right? That's the definition why we're like, what do we mean by that doesn't really hold? So as a result of that, we know if you look at this T1 and T2, these two tuple, they must hold on alpha, right? Because alpha gamma hold, right? So if I take a subset, they must hold. They doesn't match on beta, right? Because they must match, they must match on gamma, right? So the only way that you have beta gamma and the beta gamma doesn't really hold on between T1 and T2 is for beta doesn't hold. doesn't match. You have these two tuple match on alpha, but doesn't match on beta, right? But this contradicts with your assumption that alpha to beta hold, right? So essentially, this gives you a very simple proof about the soundness of this augmentation rule. Any questions so far? Any questions? Okay. And you can do the similar exercise for transitivity, right? Again, what does the rule tell you? It will tell you that if you have alpha to beta and beta to gamma, you have alpha to gamma. Okay. So how can you prove this is sound? Yeah, again, right? So from alpha to beta, right? So what do you know? You know that for all possible two tuple, for all the pairs, if they match on alpha, it implies they also match on beta. That's what alpha beta tell you, right? What do you have if beta to gamma hold, right? So that actually means for all possible tuples in this instance, right? If they match on beta, they also match on gamma. You put this together, you get for all tuples, if they match on alpha, that implies it's also match on gamma, right? So that's actually the soundness proof of the inference rule. So as we can see, these three inference rules are actually sound. If you give me a collection of functional dependencies that actually hold in your relation instance, you can apply any of these inference rules to get a new functional dependency that will also hold, because that's semantic sound. And you can apply that again, which give you a new one, which also will hold. Okay? The soundness part is relatively simple for this inference system. So what's amazing about this is the inference system that you can construct using these three different rules are not only sound, but also complete. And that's actually a surprising part, because they are so simple. Complete means that if for all the possible rules that hold on this instance, they can be derived by simply applying these three different inference rules again, and again. So that is actually something surprising. So now let's try to think about completeness. So this is just the definition of the soundness part. When you go back home, like read that precisely, it should be easy to understand. Now let's try to understand completeness. So what do you mean by completeness? Let's try to define that precisely, right? So it means that I have a set of functional dependency f. If f imply alpha to beta, it means that I can also derive alpha to beta from f by applying Armstrong axiom. So that's what we mean by this. And that's what we actually want to prove. So how should we think about this, right? How to prove it? So to prove it, let's try to just get back to the definition of closure, right? So essentially, you have a set of functional dependency f over R. You have alpha as a set of attributes in R. And we say the closure of alpha with respect to f, we say that alpha plus, so it's different from the closure of f that we defined. This is actually closure of alpha with respect to f. Okay? It's a set of all attributes y such that alpha decide y. So essentially, the closure of alpha with respect to f is all the other attributes, sorry, not all the other attributes, all the attributes that can be decided by alpha given f. Okay? So this is closure. And here whenever we are saying here we're talking about derivation, we're talking about syntax. Okay? So all the so y is in the closure of alpha when alpha to y can be derived from f using Armstrong's axiom. Okay? So this is the formal definition of this closure of alpha. So once you have this, the following is true. That is, if I can derive syntax applying those inference rules, alpha to beta from f, okay, then that's equivalent to say beta is a subset of the closure of alpha with respect to f. Okay? This hold. Then. So let's try to think about it. Right? To prove this is actually kind of simple, right? So let's try to prove from the left-hand side to the right-hand side. So what should we do? You assume that you can derive alpha to beta from f, and then you take any attributes y in beta, right? So you have that you can derive beta to y from f. Why? Because you can actually apply the reflexivity rule, right? And then you get this. And then you apply the transitivity rule by putting the first two rules together. You have essentially, you can derive alpha to y. So that's actually give you the proof from the left-hand side to the right-hand side. And then for the other side, you can also prove that. The proof is pretty natural. It's very hard to describe in like 2 minutes, but when you go back home, just read these 3 lines. So it will be very natural to see how to prove the whole thing from the right-hand side to the left-hand side. But trust me first, assuming this is true, okay? If you can derive alpha to beta from f, that is equivalent to say beta is part of the closure of alpha with respect to f. Okay? Now the complete proof, we are not going to like go through this, but when you go back home, try to read it. It should be pretty easy to understand. So all you have to do is to suppose that you have an inference rule, alpha to beta, that hold semantically, but you cannot derive it. So to try to assume that, and then try to derive some contradiction by constructing a relation instance, right? That gives you contradiction. So that relation instance is going to look like something like this. Okay? So again, we are not going through this during the lecture because this is something you need to sit down, read and think for 20 minutes, and then whole thing become relatively natural. It's very hard to communicate that just in like a couple minutes. But again, trust me, okay? This system is sound. I think I can convince you that at least, but it's also complete. Okay? So what's interesting, once you have this inference system, you can start to derive other rules, other inference rules for functional dependencies using this Axiom system. So you could have the union of functional dependency, for example. If I have alpha decide beta and also alpha decide gamma, essentially that also means alpha decide the union of beta and gamma. Okay? That sounds very natural. But then you can prove this very precisely using this inference system. We have alpha decided beta, which is given in the condition. And I have alpha decided gamma, which is given in the condition. Right? I can do, for example, augmentation. Right? I can take the second rule. I just add alpha to the left-hand side and to the right-hand side. Then I have alpha also decide alpha and gamma. Alpha union gamma. Okay? And then I can do the augmentation for the first rule. I can add gamma on both hands. Right? I can add gamma to alpha, I add gamma to beta. I have alpha gamma, decide beta gamma, and then you do the transitivity of this. You get alpha decide beta gamma. Right? Once you have this inference rule with 3 very simple rules that both sound and complete, you can start to derive new inference rules for functional dependency relatively easily. Okay? And there are other rules. There's another rule called decomposition that looks like this. It says like this. Assuming you have alpha decided beta gamma, okay? That implies alpha decided beta and also alpha decided gamma. Okay? So again, this one is relatively simple to prove. You have alpha decided beta gamma, which is given in your condition. So what should you do? Right? You have beta gamma decide beta, reflectivity, because the right-hand side is a subset of the left-hand side. And then you have transitivity, it's done, right? So you can similarly do alpha to beta. They're very simple, right? Once you have this very simple inference system. And because it's complete, because it's sound, you don't need to worry too much when you apply it. And you can derive other rules that get a little bit more complex. There's one rule called pseudo transitivity. So it looks like this. So you have one functional dependency from alpha to beta. Alpha decide beta. And you have another functional dependency, beta gamma decide theta. Okay? It got a little bit tricky now. Given these two, you have a new functional dependency, which is alpha gamma decides theta. The proof of this will take a little bit more thoughts. So what should we do? If you look at this intuitively, right? If you want to get the place that you can have alpha gamma on the left-hand side, right? Probably you also, and you want theta on the right-hand side, you probably want to do some transitivity, right? And apply that to the beta gamma to theta rule. Because otherwise there's no way I can get theta on my right-hand side, right? The thing that I really want to prove is alpha gamma to beta gamma. If that is true, I can do the transitivity, and the whole thing is done. How can I do that? How can I say alpha gamma derive beta gamma? Well, I can augment the first rule by putting gamma on both sides, right? In this case, what I can do is I have alpha to beta, I put gamma, and then I know beta gamma to theta, then it's done. Okay? So this is called pseudo transitivity, right? If you have alpha to beta, beta gamma to theta, then you have alpha gamma to theta. So any questions so far? So far, so good? A little bit dry, but essentially, we define two different notions of what do we mean by kind of a set of functional dependency, imply another rule, or what do we mean by you can derive them. We define three different, very simple inference rules. They are sound and complete, and you can use them to derive other rules. That's pretty much what we have at this moment. Okay? Any questions before we move on? No? No questions? Okay. So there are more about closure. There are actually more interesting about closure. So here we define closure of a set of attributes alpha with respect to a set of functional dependency, right? So call that alpha plus is set of all attributes y, right, such that you can derive alpha decide y, right, using f, right? So given f, because set of functional dependency over R, and given alpha as a set of attributes, how to fund this closure, right? So yeah, so there could be multiple things you can do, but there's a actually relatively natural algorithm for you to actually fund this closure, okay? So the thing that you do is you start by setting this closure to alpha, okay? And that's the starting point. Because, yeah, so all the attributes in alpha will also be in that closure because, yeah, right? So, and that's natural, right? So, and then you repeat the following. That is, for every single functional dependency you have, for example, beta to gamma in F, if beta is a subset of your current closure, okay, and then you put gamma to your closure, make sense? And you continue to do this until your current set of closure doesn't change, and then you get your closure. Make sense? This is a very, very simple algorithm to say this is set of functional dependencies. This is a set of attributes. The closure of the set of attributes can be you can find that by running this very, very simple algorithm. It's also very easy to see why this is correct. Okay, so I mean, when you go back home, try to read this algorithm, and it should be easy to prove that this algorithm that gave you the closure of alpha with respect to f. Okay. So if you think about why we care about closure so much, it's because once you can find the closure, you can actually use it to do a whole bunch of things. For example, if I have f as a set of functional dependencies, I have alpha to beta, and I say, yeah, how can we check whether you can derive alpha to beta from f? Well, the thing you can do is to first compute the closure of alpha using the previous algorithm, which is very simple, right? Compute the closure of alpha and check whether gamma is in the closure or not. If gamma is in the closure, it means that you can actually derive alpha to gamma from F. Otherwise, you cannot. Okay? Once you have this very simple algorithm to compute the closure, you can actually use it to check whether you can derive a functional dependency rule from a given set of functional dependency rules. And you can use that to do other things. I have two collections of functional dependencies, F and G. Whether I can derive G from F. Okay? Whether, yeah, so I'm saying like the way to do it, right, is you enumerate all the rules in G, right, and you check whether you can derive that from F by computing the closure of the left-hand side. How can you check whether F and G, two collection of functional dependencies, are equivalent, for example? Well, you check whether you can derive F from G and you can derive G from F, and that's it, right? Once you can compute the closure of a subset of attributes, answering these questions are very simple. Compute the closure and you check, okay? And as you can see, these are very fundamental questions. So, and you can do more. Now, assuming I give you a relation R, how to check a subset of attributes K is a super key or not? And that start to look a little bit useful, right? So how can I automatic, systematic check whether a set of attributes is a super key or not, given the functional dependency I have on the schema? Essentially, you are trying to check whether you can derive the functional dependency that K decide R, the whole set, from F. And what should you do? You are going to compute the closure of K using that very simple algorithm, and you try to check whether that closure covers all the attributes in R. Once you are able to do that, that subset of attribute K is a super key. Okay? And then this also gives you an algorithm to automatically decide, given a set of functional dependencies, whether a subset of attributes can be a candidate key or not. It needs to be a super key. It needs to be minimal. Okay, make sense? What do we mean by minimal? It means that if I remove any attributes and recompute the closure, I cannot cover all the attributes anymore. Okay, so and then this gives you a very precise algorithm to compute all the possible candidate keys in your relation. So far, so good. Any questions? No? Okay. So another thing that we could do. So here we think about, actually try to think about what is all the possible functional dependencies that we can derive. I think we are pretty good at that at this moment, right? So, and now, if I give you a collection of functional dependencies, I also want to reason about the redundancy between those rules, right? Because I could have multiple rules in this site, but maybe I do not need all those rules to describe this site. Maybe there's a minimal basis that I can actually make the site a little bit more compact. So, and that's what we are trying to understand, something called minimal basis and minimal cover. Assuming we have F as a set of functional dependencies, right? So just look at this very simple example. I have A decided BC, B decided D, and A decided D, for example, right? So if you look at this is actually not that unique in the sense that I do not really need A decide D, because I can derive that from the first two functional dependencies, right? So there are actually redundancy here. And how can we simplify this F to remove those redundant functional dependencies? So essentially giving F a minimal cover of F is a set of functional dependencies, G, that has a following property. First one, G need to be equivalent to F. I want to simplify F. I don't want to change F, okay? G need to be equivalent, which means that, right? So given f, you need to be able to imply g. Given g, you need to be able to imply f. This is a semantic level. On the syntax level, is for every single rule in g, you should be able to derive that from f using Armstrong's axioms and the other way around. Okay? G and f need to be equivalent. If g wants to be a cover, I think that makes sense. And all the functional dependency in G has the following form. It's always from X to A, where A is a single attribute. The right-hand side of all the rules in the cover need to be a single attribute. And the third thing is not possible to make G smaller, meaning that if you remove any rule in G, it will not be equivalent to f anymore. Okay? So if you give me a set of functional dependency f, the minimal cover of it, G, need to satisfy these three actually very natural conditions. Right? So G cannot be made smaller. So how to compute this minimal basis or minimal cover? This is actually a very simple algorithm for that. So essentially, the first step is you take your original site of functional dependency f, and you decompose it. You decompose the right-hand side to have a whole bunch of rules with only a single attribute on the right-hand side. Okay? So let's say G is that set. Okay? By decomposing the right-hand side into a single attribute. The second step, you remove all the functional dependencies are trivial. What do you mean by trivial? The right-hand side is a superset of the left-hand side. Sorry. The left-hand side, this side, yeah. So the left-hand side is a superset of the right-hand side. Okay? So that functional dependency is trivial. You remove all of those. And then you remove all redundant attributes from the left-hand side of the functional dependency that you do not need. Okay? So how to do that? If I have a functional dependency x to y, you take each attribute, small x in x, you remove that, and you see whether you can still imply x to y. If you are able to do it, it means this x attribute doesn't need to be there. You will remove it and replace your functional dependency with a simpler one. Okay? And then the last step is now you have this set of functional dependencies. You remove all the functional dependencies are the same with each other. You remove all the redundant ones. And then that gives you the minimal basis. So this is actually very simple. Okay? So this is just one example. Let's look into this. Assuming I have f has 4 different functional dependencies, A, B to C, A to B, C, B to C, A to B. How to compute the minimal basis of this thing? The first step is to decompose it to make sure every single rule have a single attribute on the right-hand side. Right? In this case, what we are going to do is take the second rule, A to B, C, right, and decompose it. Now I have A to B and A to C, and all the other rules stay the same. Okay? So encoded by different color. This is step 1, okay, and nothing else. And step 2 is let's try to remove all the functional dependencies that are trivial. In this case, there's no trivial functional dependency, so it's fun. And then step 3 is try to remove redundant attributes from the left-hand side. In this case, right, if you look at the first rule, A, B to C, and we try to think about, is all the attributes on the left-hand side really necessary? What if we remove A from the left-hand side? What if you only have B to C instead? Can we derive A, B to C from that? Right? So in this case, right, if you go back to the inference system that we have, this is something that you are able to do. You can actually derive A, B to C if you only have B to C in your set of functional dependencies. Okay? So this is actually something that you are able to do in this case. And then what I'm going to do, you are going to remove A because it's not that useful. And then once you have this, you can see, yeah, I actually have redundant functional dependency. That's step 4, right? I have B to C appear twice. I have A to B appear twice. I remove those redundant things. I get something like this. So this is just one example about how to derive the minimal basis given a set of functional dependency, right? And get something that's much smaller in two sense. Each rule is smaller, right? And second, the number of rules, right, is also smaller, right? A simpler set of functional dependencies describing the same thing, okay? So this is the minimal basis algorithm for this. So again, like this lecture is probably the most theoretical lecture of the whole course for this semester. So the best way to do it is when you go back home, really read all the slides, right? So and understand what we are really talking about here, and also to actually practice some of the algorithms. Okay, so if you go to this website, it's actually a very interesting website. So if you go to this website, you can actually put in a whole bunch of functional dependencies, right? And then you can ask it to say, compute the minimal cover. It's going to actually show you step by step of the algorithm, right? So you can play with different set of functional dependencies and try to see whether your understanding is correct or not. Okay? So best way to learn about this lecture is go back home, read the slides, and practice. And if you have any questions, yeah, just post questions on Moodle or just send me an email, right? So look, like it looks a little bit theoretical, but it's actually not that hard. Okay. So now we know about functional dependency. We know how to compute about the minimal basis, right? So now let's try to use this language, this tool, to reason about something that more relevant to our relational model. So the thing that we want to reason about is when you decompose one relation into multiple of those relations, what can we say about that decomposition? And you are going to see how this notion of functional dependency falls into what we can say. So, and the reason we want to talk about it is, as you are going to see, many by design, okay, logically, they often combine multiple concepts, right? So remember the student's course and the address relation, right? And that's a relation contains two pieces of information, right? We should actually decompose it into two different relations. One stores the student and the course, another stores the student and address. So we want to reason about decomposition to make sure we have one concept in each of these relations. The formal way to talk about decomposition, it looks like this. Assume I have a big relation R, and I decompose it by attributes, okay, into a whole bunch of smaller relations, R1 to Rn. So there are multiple properties that we want to say about this decomposition. We say this decomposition is lossless. I'm not losing any information by decomposing it, only if the following hold. That is, if you do a natural join of all these n different relations, R1 to Rn, you get your original relation. Okay? If this hold, we say the decomposition is lossless. Okay? And second, a decomposition could preserve all the functional dependencies. That's another property that we kind of want to reason about. So we say this is true if and only if that you take all the functional dependencies that hold for R1 and hold for Rn, and you combine them, you compute the closure. It's the same as if you take the functional dependencies of the big relation and you take the closure. Okay? So these are the two properties that we are really curious about when we talk about decomposition. So first question is, when is the decomposition lossless? When can we decompose a bigger relation into two smaller ones? So let's say you have relation R look like this. Yeah, two sets of attributes, R1 and R2. Okay? So consider decomposition of R doing this. I project R into R1 as a subset of attributes, right? That gives me R1. And then I decompose this R, right, on R2. This gives me these two different kind of smaller relation, R1, R2. This decomposition lossless, meaning that if I do a natural join between R1 and R2, I'm going to get the original R. This decomposition lossless if and only if you have functional dependency from the intersection of R1 and R2 to R1, or you have another functional dependency from the intersection of R1 and R2 to R2. Okay? The way to think about it is this is all the possible attributes. You have one subset which is R1, you have another subset which is R2. And the intersection, for example, let's call that beta. If you have a functional dependency from beta to R2, or you have functional dependency from beta to R1, if beta decide all the things you have in R2, or beta decide all the things you have in R1, you can actually decompose this relation into one relation with only R1, another relation with only R2. So this is intuitively what this is saying. And now you can write it down in a very precise way using the language of functional dependency. And this is just one example. Okay? So let's look at this decomposition. I have an input relation. I have a pub, I have a guest, I have the beer, the guest leg. Okay? So, and then what if I decompose this into two different relations, right? So I say this is a visitor of the pub. Right? This guest visits that pub. And then I have another relation called drinks. Okay? So a guest drink beer, right? Different type of beer. So this is one decomposition. Okay? I can decompose the drink relation into these two smaller ones by projecting that onto different subset of attributes. And then I can join the back, right? I join these two smaller ones to have the one on the right-hand side. So as you can see, is this decomposition lossless? It's not, right? Because if you compare the thing after join, and if you compare that with the original relation, they are different. I mean, I get two more tuples, right? So this join is not lossless. If you think about why it's not lossless, we want to be able to reason about that without doing this join, because it's super hard to do. Can we reason about it without running this decomposition? Well, the reason it is not lossless is you do not have any of these functional dependencies in your system, in your original relation. Right? You do not have guest decide beer, because if you look at the guest D, right, so that person drink two different type of beers. Right? You do not have guest decide pub, because if you look at the person D again, that person go to two different pub. You do not have the functional dependency that the intersection of the two decompositions decide one of them. Okay? Because you do not have this decomposition is not lossless. You do not even need to run this process. You will know whether you are able to decompose this bigger relation in a lossless way. And that is why we care so much about functional dependency. Because that gives you a way to decide lossless decomposition as one application. It can do more things. But even this, I hope, it justifies why we go through this full process, defining it, understanding how to reason about it, right? So it's just one example. Any question about this? Is it clear? Lossless decomposition. Why do we even talk about functional dependency, right? So how can we decide the decomposition is lossless? We see whether it can derive any of these two functional dependencies. How can we decide whether it can be derived? You compute the closure, you test whether it's a subset. How can you compute the closure? We have the algorithm, okay? Clear. Why can you do this? Because the Armstrong's axiom are both sound and complete. That is why you are able to do this without thinking too much. Okay? That is, if you remember one sentence from today, that is what I wanted to remember. Okay? So now we can look at another decomposition. So we have father, mother, and child. You can decompose that, use this parents relation, into two smaller ones. father contains father and child, mother contains mother and child. In this case, if you join back, you'll see, it's actually lossless. Because if I join the two smaller ones into a bigger one, that's the same as my original relation. Why? Because in this example, you have this functional dependency child to mother actually hold. And because of that, without running this decomposition, you can actually know this decomposition will be lossless. Okay? Again, you also have this another functional dependency hold. You only need one of these to hold. Okay? For the loss to be for decomposition to be lossless. But in this example, you have both hold. Okay? So that is actually why it's interesting. And in this decomposition, child will be the key for actually all these relations. Okay? Make sense? That's about functional dependency. That's all for today. On Friday, we are going to talk more about functional dependency and normal forms.